we are happy to have Zimu Zhu, who is visiting assistant prof with us starting this fall. And he will talk about his research on topics on principal agent problem and optimal portfolio problem. So Zimu, the screen is yours.
Thank you. Thank you very much for Professor Fox's introduction. Thank you very much for sharing the opportunity. For giving me the opportunity to share basically what I did during my PhD study. So today I'm going to introduce two projects I did in my PhD study. So one is the principal agent problem. It is joint work with Professor Jianfeng Zhang, my advisor at USC, and another is an optimal portfolio problem. It is joint work with Professor Wei Dongtian at UNC Charlotte. So the first project, a dynamic principal agent model, indeed was presented in the 10th Western Conference of Mass Finance. And so if you join that meeting, so this part is not new to you, okay? So for this problem, let's first take a look at a very brief introduction of the principal agent problem. So for the principal agent problem, so typically there are two parties. One is the principal, and another is the agent. Okay. So sometimes there are not only one principals. There are some also there are some cases there are many agents. So in this work, we will focus on the case there is only one principal and many agents. So the principal's control is a contract. So this contract will provide incentives for the agent to work for her. So basically, the agent will receive the contract from the principal, and he will work for the principal. And the agent's control is his effort process. So given the contract the principal offered, the agent will choose the best effort for himself, so for the agent. So there are like several types. For example, if the effort can be seen, whether can be seen from the principal's view. So basically, in our project, in this project, we will focus on the most popular way is so-called moral hazard or hidden action. So basically, the agent's effort process cannot be seen from the principal's view. But of course, the agent himself know everything, know the effort process. So the principal agent problem is a so-called Schellenberg game, so which forms a bilevel optimal control problem. So basically, once the principal gives C, let's say the contract, then agent will choose his effort. So if this is the principal, if this is the agent, then agent will choose his optimal effort process. So it's a bilevel optimal control problem. So when we formulate the problem, the principal is the first mover. So he will first decide the contract, and agent is the follower. So this is so-called Schellenberg game. But when we solve the problem, we will first solve the agent's problem. So basically, we solve backwardly. So first solve the agent's problem, and then solve the principal's problem. So there are huge literature for principal agent problem. Maybe let me do a very fast review. So, but of course, it's limited. So first, the researchers start to study discrete time model like Ross, Holmstrom, Rogerson. And later, researchers start to study continuous time version. So, and it is interestingly that continuous time model for principal agent problem is easier to study than discrete time model. A breakthrough is by Holmstrom Milgram. So I think they won Nobel Prize by their work in principal agent problem. And in continuous time model, basically we have two different cases. So one is the so-called lump sum payment. So lump sum payment is the payment is just once paid at terminal time t. So after Holmstrom Milgram's work, there are some other works like Shuttle and Son, and Svitanik and Zhang has a book, and Svitanik, Posama, and Tuzi, and there are many other works. And also another way to study it is continuous time model as well as with continuous payment. So continuous payment, of course, means that in the contract period 0 to T, so it's paid continuously. So it's a contract something like this. Let's say is 0 to T alpha T dt. So it's paid continuously. But this is only paid at capital T. So a very interesting work is by Sonikov, 2008, and also Williams, 2015. In his paper, I think he derived some explicit solution, so under his framework. And also recently, Posama and Duzi, they have a paper. I think they basically give some rigorous proof for Sonikov's model. Okay, let's see our model. So basically, in our model, we will use the continuous time model with continuous payment. So we will use this one. Okay. So let's say the continuous time model is like we study the problem on the weak formulation on 0 to T. So mathematically, it's like the probability measure is also the agent's control. So let's assume the output process is a Brownian motion on the fixed probability space, and the agent controls the distribution of xt. So, and we denote it as PA. Then if we use Casanov's theorem, then we can write this as AT dt plus sigma dBTA. So just simply by Casanov's theorem. So under the weak formulation, under the new probability measure, the contract will become, the output process will become this effort process plus Brownian motion. So it's PA almost surely. So then we will introduce a continuous payment problem to illustrate the timing consistency. So basically, this is the main object of the first project in the next page. Okay. So for a continuous time model, so let's consider a continuous payment problem starting at time 0. So the agent's problem is like if we are given continuous payment alpha t, so it's this is from the principles part 0 to capital T alpha t dt. The agent's control is his effort process, this AT from 0 to capital T. So he wants to maximize the utility function. This is his value function, so this is the utility function. So 0 to T UA alpha T dt, this is what the agent gets from the principal, and this UA is the so-called utility function, so which is increasing and concave. So there are many like utility functions. In our project, we will use simply this one. So we will see that this function clearly it is increasing, both increasing and concave. Okay, I think there are also some other ones like this. So gamma if greater than 0. So something like this. So this minus 1/2 0 to capital T AT squared dt is the so-called negative effects of efforts. Okay, so it's like when agent make efforts to increase the output, himself need to pay some cost. So we assume that under this framework, we assume that the optimal control A exists and it is unique. So for simplicity, we assume it is unique and it exists and it is unique. So we denote as A star alpha because it depends on this contract. And the principal's problem is after the agent chooses his optimal effort. So basically, once we first solve step 1, the agent's problem, we got this A star alpha. Then the principal wants to maximize her utility function. So by this. So first, this agent will determine the probability measure, the A star alpha. And clearly, this part is easy to understand. So this is the contract the principal will pay to the agent. And this part, basically, if we take a look, it's almost equivalent to x capital T. So because this xt is this one, so we know that xt basically equal to 0 to capital T AT dt plus 0 to T, I think it's sigma dBTA. So because here we use the risk neutral measure, so after we take expectation, this part will disappear, right? So there's only one function here. So this is the principal's problem. So this part basically is the output minus the contract she need to pay to the agent. And in the principal's agent problem, we need to subject to the individual rationality condition. So given a contract, at least we need to make sure that agent will get something, so that agent will work for the principal. So we assume that at least when the agent chooses the best effort for himself, he can at least get a particular number R. So this is the model setting. So then let's see what is the so-called time inconsistency. So indeed, above problem is solvable. So the time inconsistency in a principal agent problem means the optimal contract at time 0 is not optimal at time t anymore. So let's see. So if at time 0, if this is the 0 to t problem, and at time 0 this is this is the participant individual rationality, or say the participant constraint R at 0. So we solve this problem, first solve the agent one, then solve the principal one. We'll get the optimal contract for the principal. And let's see if in the middle, in the little, for the time at little t, so we solve this problem again, still with individual rationality R, but that is for time little t. So we'll get another optimal contract for the principal, let's say alpha theta star. So in general, these two are not equal. So this is so-called time inconsistency. So even we assume this R be RT, or even like we make it randomly, we make it like a stochastic, most cases, these are not the same. Still not the same. So there is an explicit solution. There is an explicit solution for the lump sum case in, I think, Chen, Du, Ma, and Zhang in their paper. They construct an example which can be solved explicitly. So for that C, that is the lump sum case. You can easily see, directly see that it can be explicitly solved that they are not equal. So however, in real life, it is quite common that the agent may quit, or the principal may fire the agent during contracted period. So our goal is to construct a dynamic time consistent principal agent model. We take the equilibrium approach in our model. So our idea is we study the problem at time 0, but we take into consideration that at time t, the agent may quit. So that's basically what we thought. So let's take a look at some assumptions in our model. So we assume that there are only one principal and a continuum family of agents available in the markets, parameterized by some parameter theta. So this theta is positive numbers lie in a fixed interval. So we will use this theta to describe the different quality of the agent. And also currently in our project, we assume only the agent can quit during 0 to t. So which means currently we do not allow the principal to fire the agent. And if the agent quits at time t, there will be some quitting cost, C theta t for him. Okay, so this theta means this is the type theta agent, and t is that you quit at time t. And also in this work, for simplicity, we assume the dynamic individual rationality R theta t. So this is also for the agent type theta, and this for at time t is given exogenously, and it is deterministic. So indeed, even with this definition, the problem is still not very easy to handle. So we expect if we make a little bit change on this, it will be more complicated. And for this project, we assume the utility function take a particular form, negative e to negative x, which is non-positive throughout this talk. Okay. Okay, so our goal is to study the case that agent is allowed to quit, but we will first start with the case that agent is not allowed to quit. So this will give us some motivation and the big like the picture of this problem. So we studied the problem for the model for type theta agent. So again, this problem is very similar to what we introduced before. So the agent's problem, given contract alpha 0 to t, the agent's problem is to maximize his utility function. So this again is the utility he gets from the contract, and this is the so-called negative effect of efforts. And we use this 1/2 theta to distinguish different agents. And you can see if theta is larger, then this part is smaller, right? So the theta is larger means, okay, the agent will pay less for his cost. So again, we assume that it exists and it is unique for the optimal control A theta alpha. So indeed, in our problem, it can be proved very easily. So the uniqueness and the existence. So the principal problem, again, it's simply the output process minus the contract she need to pay to the agent. And again, subject to the individual rationality condition. So this is R theta 0. Okay. Again, so as we mentioned, so every time we first solve the agent's problem and then solve the principal's problem. So throughout this talk, we will make the following assumption of the principal's control alpha. So we assume that this alpha, for different alpha, it has a uniformly upper bound. For each alpha, there is a lower bound, but there's no uniform lower bound. So this condition indeed is very crucial in our proof of the continuity of the value function, because if we want to use the DPP to derive the HJB equation, we first need to show the continuity of the value function. So far, it seems like without this condition, we cannot prove the continuity. So, and this lower bound, of course, is for technical reason. I mean, for different alpha, we need to have each alpha, at least we need to have a lower bound. If we assume that the contract has both uniformly upper bound and the lower bound, then for this case, agent is not allowed to quit. The continuity will be straightforward. But the problem is when we solve the problem, when we solve the model when agent is allowed to quit, so these two uniform bounds will give the region something like this. And also later there will be the optimal stopping problem will give us another lower bound. Then at this intersection point, it is very hard to determine the continuity. So currently we choose not to use this condition, simply use this. Because if we only allow the principal's contract to have a uniformly upper bound, then the domain will be something like this. So it is good to study. When we solve the agent's problem, so every time like we use the multiple representation theorem to derive and then use the comparison principle of BSD. So the agent's problem can be solved easily by this. Okay, so the agent's remaining utility, optimal utility function, basically it's part of the solution of backward SDE. So by the assumption 1, so basically by this assumption, the agent's domain is D0. So it's less or equal to negative E to negative C0 T minus T. So this C0 is simply from here. Okay. And we can see the graph is something like this. So this is the upper bound, and this is the terminal time, and this part is what we want to calculate, right? Okay, so then let's see the principal's problem. So after we first solve the agent's problem, we can show that the principal's value function, this V0P, theta is for the agent's type, T is for the problem starting at T. So this X basically will represent the individual rationality. There are theta T. In the end, we'll plug into it. So we can show that this value function, it is continuous, both continuous and decreasing. And also we can show that the principal's value function, so V0P, is the unique viscosity solution of the following HJB equation in the domain of the agent, okay, in D0. So this is the HJB equation, and the boundary condition is it's not very difficult to calculate. So on the right hand side is 0. So on the top it's this one. So this is the value for the boundary condition, and what we want, of course, is something here. Okay, then we make a little bit change to see what happens for the agent is allowed to quit at most once. So let's first see the agent's problem. So for a fixed type theta 0 agent, so given alpha 0 to t, the agent's control now are two processes. So first again is the effort process, AT, and another one is the stopping time, tau. And he wants to maximize the following utility function. So let's see term by term. So the first one is if he stay in the existing contract. So this is what he will get from the until tau. Tau is the the time he choose to quit, right? So this is the one he will get if he stays, and if he quit, so basically he will immediately go to the market, and that market value will give him this. But as we mentioned, he needs to pay some cost, right? So it's a CT theta 0. This is definitely this one is a positive number. So if he quits, he go to the market, then he will get something this. Okay, so he first assume A and assume tau. So it has now the agent has two controls. So again, we assume that this indeed we can prove that the optimal control exists, and it is also unique. Next, we see that what is the principal problem if the agent is allowed to quit at most once. So currently, we assume the agent can quit at most once. So if the agent quits, the principal will hire a new agent from the market, so possibly with a different type, but which is best for her. So we will see this best basically represents the soup here. So from the principal's view, she wants to hire a principal. She wants to hire agent, but it is good for the principal. So let's see the principal's problem. So this one represent the quitting happen at most once, and this 0 at time 0, theta 0 is the first agent, and this is the individual rationality. So this part is still the same as the agent is not allowed to quit. So this is the output. This is what the principal needs to pay to the agent, and until the stopping time tau, until the agent leave. But after the agent leave, if this happen, then the principal will hire a new agent. But currently, we assume the agent is allowed quit at most once. So after this quitting happens, there will be no more quitting. So we can use this V0P. So possibly with a different type theta, and this stopping time tau is determined by the first agent, right? So it's tau theta 0 alpha. And this is the individual rationality for the new agent theta, but with the time is still tau, right? Determined by the first one. So still subject to the individual rationality of this one. Then let's see. So first we solve the agent's problems. So since now we have optimal stopping and also optimum A, so this will give us by using a comparison principle of backward SD, and since we have optimal stopping, So the agent's optimal utility can be characterized as the following reflected backward SDE. So it's like this. So the solution of this reflected backward SDE is a triple. So it's a Y, Z, and K. So K is some non-negative increasing process. So we have a lower bound for this Y. So indeed, this L theta 0T will give us will make the lower bound for the domain of the agent. And the third condition is the so-called square hold condition. So this will like define the solution. And this tau can be determined by the first heating time of YT hit this lower boundary. So this is like the standard theory from RBSDE. Then from this way, indeed, there's we prove a proposition there. So basically, there's a one-to-one correspondence. So the original problem is backwardly, but we can show it is equivalent to a forward one. So therefore, the agent's domain is something like this. So less or equal to negative e to c0 t minus t greater or equal to lt theta 0. So indeed, this part, and this part are the same. So the only difference is now we have a lower bound. Okay. So then we solve the principles problem. So after we first solve the agents problem, we can show that again the value function, this v1p, so 1 represent quitting happen at most once. It is continuous and decreasing in x. And the principles value function, so v1p, we can show that it is the minimal viscosity solution of the following HJB equation in D1. So this is negative. So here, let me use another color. So here is negative C0 T minus T. This is 0. And on the boundary, so we will indeed use the solution of the first part. So remember, we first solve V0P. And then when we solve V1P, we will use the condition we will use the result from the V0P. So unfortunately, so far we can only derive the boundary condition is this U greater or equal to this one. We cannot exactly know what is the boundary condition. That's why so far we can only show this the minimal viscous solution satisfy the following boundary condition. So this case already gave us some important information. So first, the value function is v1p theta 0 tx is not continuous at the lower boundary x equal to L theta 0 t. So basically, at this part, it is not continuous. But we know that since this value function v1p theta 0 tx is decreasing, so decreasing means so this is positive way. Okay, so decreasing, then if x decrease, then the value will increase, right? So the value increase and it's monotone, though we know that, okay, this limit indeed exists. So although it might not be equal to the value on the boundary, but at least we know the limit exists. So the value function will become continuous after facelifting. If we use this limit, right, then become continuous. And also it is possible that with quitting, it is possible that the value function is greater than the one without quitting. So it's like, because although we allow the agent with more freedom, but in the market we hire possibly we will hire a better one. So it's possible that V1P is greater than V0P. So however, in the extreme case, if there's only one agent, and if he quits, we need to hire him back. And if the cost is 0, then basically the cost of quitting will transfer to the principal side. So in this case, indeed, we have a V1P less than V0P. Okay, then let's see if we make the model more general. So if we see if the agent is allowed to quit multiple times. So two cases. So first is the model when quitting can happen at most n times, fix the number. Of course, another case is the quitting can happen infinite times. So if for at most n times, so this is very similar to the case at most once. Okay, so let's see. Indeed, the agent's problem is like the same, because from the agent's side, his only choice is to whether to quit, right? So again, so given alpha 0 to t, the agent's control is effort process at, and the stopping time tau. So two controlled process, and he wants to maximize this value function. Again, so this is the utility function he stayed. This is the utility function he quits. Okay, and again, we assume the optimal control A and tau exists. So this is the same as the previous one. For the principles problem, we only make a little bit change. So this Vn, this n means that the quitting happened at most n times. And also this is what the first agent, the existing one, will give the principle. And after the first agent quits, so since we allow the quitting can happen at most n times, so for the rest of the time, the quitting can happen at most n minus 1 times. So therefore we can use the previous result. We can use the previous result, right? So previously this is V1, this is V0. Now we simply make it Vn and Vn minus 1. Okay, so this theta is like still we can choose from the best agent from the market. And again, indeed, this boundary condition is also this individual rationality is still the same because it worked for the first agent, so it must be greater or equal to some particular number. So let's see. So indeed, this case is very similar. So when we solve the problem of the principles, so again, after first solving agent problem, we can show that the value function for the principle, again, it is continuous and also decreasing. So again, this x is r theta 0 t. Okay. And again, the principle's value function, VNP theta 0 tx is again a minimal viscosity solution of the following HJB equation in D1, Dn equal to D1. So domain is the same indeed. HJB equation is here, and the boundary condition is this. So again, previously we used V0P here, now we use Vn minus 1. So for this problem, it's like every time we first solve V0, then we use V0. After we take soup, will become the boundary condition here for the next problem. Okay, so it's like we can solve recursively. Okay, so next I will just briefly introduce what is V infinity. So indeed, we didn't give the rigorous definition of what is the V infinity. But in our paper, basically, we define it in a way that quitting can happen infinite times. And indeed, we have the following properties of V infinity. So first, V infinity is indeed the limit of Vn. So this is as it should be, right? So it and second, there's a very interesting result. So if the cost has a uniformly bound for all the agent and for all time t, which is greater than 0, then we can prove that the quitting will happen indeed finite times. So it's like, although we allow the agent to quit infinite times, but if the quitting cost has a uniform lower bound, then the quitting will happen indeed finite times. So by this characterization, we know that we can calculate V infinity by the limit of Vn. But on the other hand, we can calculate V infinity by itself. So we can show that V infinity is also the minimal viscosity solution of the following HJB equation in D infinity equal to D1 here, D infinity equal to D1. So this is the HJB equation and with this boundary condition. So we can see this boundary condition is a little bit different from the previous one, because previous one, so U is, let's say, Vn minus 1 or V0. This is exhaustively given. But in this case, this solution is indeed part of this boundary condition, right? So the solution is also in the boundary condition. So this is a little bit different. So that's why indeed in this one, we define the minimal viscosity solution in a little bit different way. Okay. So some possible future work is it is also reasonable to allow the principal to fire the agent, but that one we expect will make the problem much more difficult. So this will add in additional game feature into the problem, and we anticipate the solution will face more severe discontinuity even after facelifting. So it is still discontinuous. Then we need to consider discontinuous viscosity solutions. And also in the current work, we assume the market value is exogenous given, so it's R theta T. So also it is deterministic, but it will be very interesting to derive this endogenously through the competition of many principles and depending on the agent's past performance. So basically we can use this. So for example, for the type theta agent, we can take a look at his output, and then we decide what is the individual rationality. In the model, we can calculate it in this way. Because from market's view, the principal may take a look at how the agent worked before, right? So then we hope that techniques in the mean field game literature will be helpful for this analysis. Okay, so this is basically the first project. And then we introduce the second project, a portfolio choice problem on the risk capacity constraint. So indeed, for this problem, we study the classical Merton's investment problem. So this one is not new, very classical. So it's the Wells process dWt equal to xt mu dt plus sigma dBt. So basically, this is what we get from the stock, and minus ct dt, this is the consumption, starting with W0 equal to W. So BT is the Brownian motion, WT is the Will process, and for this problem, we make all the parameters easy. They are just positive constants. And from the investment view, so two controls variables. One is the consumption C, another is the X. So C is basically the consumption process, so it is non-active. And XT, so if we write in this way, so this is the amount of dollar investing in the market. So I think in Merton's paper, he writes something like this, then this is the proportion he invests to the market, right? But now we simply use XT. So this is simply represent amount of dollar. And our goal is to optimize the following problem. So this value function equal to max. So U is a utility function. In our problem, indeed, we'll make it a particular form, the CRRA utility function. So for both consumption and the wealth. And of course, we assume that alpha, beta, they are two non-negative constants, and such that the wealth process is greater or equal to 0. So this is the so-called no arbitrage condition. So indeed, previously, I think usually people study these two problems separately. So either this one or this one. Okay. So basically, throughout this talk, we assume the utility function takes this particular form, CRA. So it's x1 minus r, x1 minus r over 1 minus r, where r is a positive number. So we will study three different cases for the admissible set of x, because for C it's just a C greater or equal to 0. So we will treat different cases for x. So first is x is, there's no constraint for x. X is in between 0 to infinity. So indeed, if we assume negative infinity to positive infinity, these two cases are the same because we will easily show that optimal x is positive. So first the case we will study that it has no constraint. In this case, when alpha equal to 1, beta equal to 0, so basically if there's only consumption here, this is the very classical result from Merton. And if there's only Wells process there, alpha equal to 0, beta equal to 1, basically if there's only here, then, sorry. So this already being studied in Liu and Lowenstein. So indeed, in these two cases, exclusive solution exists. Okay, even with alpha greater than 0, beta greater than 0, the exclusive solution will be easy to derive. indeed, in our paper, we derived that. That's very easy. So another possible constraint is for x is proportional, has the upper bound proportional to the Wells process. So in this case, explicit solution can also be derived. So indeed, Villa and Zaropopolo derived the case for alpha equals 1 and beta equals 0. So this is like just for this utility function. Okay. So indeed, we can easily show that if with no constraint, that x star is mu over sigma square r. So for this case, it is meaningful to, maybe I use another color. It's meaningful to assume that b less than this one, right? Otherwise, if b greater than this number, then optimal one is still this. There's nothing new there. So in the case 2, we will study. We will make an assumption like this. And indeed, our paper mainly focused on the case that it has uniformly upper bound and lower bound. Xt is greater or equal to 0, less or equal to L. So the amount of investment dollars has a uniformly upper bound. In these cases, we think that explicit solution will not exist. So the rest of this talk will focus on case 3. Okay. So our first characterization is very standard, straightforward. We can characterize the value function VW as a unique viscosity solution of the following HJB equation. So this part is standard. So so now the question is, can we have further information on the value function? So after we characterize a unique viscosity solution, can we have further information? So first, we define what is so-called constrained and unconstrained domain. So we define unconstrained domain by this. So basically, it is, so we can see the x star. So this is like negative sigma square v double prime mu v prime, right? Because this is in this part, it is a quadratic function of x, right? So the x star can be derived easily. So there are two cases. If this is greater than L, then we need to choose x star equal to L, right? If this less than L, then we can use this one. So basically, this is the idea. So we define the unconstrained domain, then we can simply use this. So if it is less or equal to L, then in the unconstrained domain, the value function satisfies this. Okay. So for this one, we can directly plug this into here. And the C part, every time we do not need to worry that just the first order condition will give us this. And since this U take the particular form, so we can derive it easily. So this is the basically the ODE in the unconstrained domain. And similarly, we define what is the constrained domain. So if this is greater than L, then we cannot take x star equal to this, right? We need to put x star equal to L here. Then we'll make the HJB equation like this. It reduced to second order ODE, right? So when alpha equal to 1, beta equal to 0, basically that's the case that is only something like that. Let me see, what is the notation I used previously? E to negative delta t. Okay. If the utility function is just like this, so indeed Villa and Zaropopolo in their 1997 paper, they show that under the constraint xt less or equal to k wt plus L. So they use a different constraint. There exists a unique W star such that the unconstrained domain is simply 0 to W star, and the constrained domain is W star to infinity. So this gives us more information on what is the value function looks like. So maybe let me first say that their constraint kwt plus L, right? And our constraint is xt And our constraint is less or equal to L, greater or equal to 0. So our case is not included here, right? If their constraint is like this, then our condition is simply included here. But so their condition is like this because the proportional, then there's other properties. So if k equal to 0, then it's totally equal to 0, right? So there's cannot be in this case. So indeed, in our work, so we show that this is also true in the following cases. Unfortunately, we still need to separate the two utility functions. So either beta equal to 0 or alpha equal to 0. So for the case that alpha equal to 0, alpha equal to 1, beta equal to 0, basically the consumption, the utility is consumption. One possible way is to simply modify Vila and Zaropopoulos' work. So their work rely on in the unconstrained domain, there is an explicit solution. So when we treat the case that alpha equal to 0, beta equal to 1, so basically the utility function is something like this, then their method cannot be applied. So we use a different method. We call it operator method. So basically we use the comparison principle for ODE to derive. And also our method will work for this case. Will also work for the first case. So if alpha and beta are both non-zero, so far we do not have a satisfied result, but we can derive a condition, the so-called single crowding property for some particular function. But that one so far is not easy to verify. So I think it still remains open. So can we show that if alpha and beta are both non-zero, then is this characterization still true? One byproduct of this characterization, this 0 to W star and W star to infinity, is with the help of this, we can also derive some numerical results. So let's see. So this model, which means that case 3, okay. So it's the xt greater or equal to 0, less or equal to L. And this benchmark is case 1. So there's no constraint. And this BPC is the so-called bounded percentage. So this is simply case 2. So xt greater or equal to 0, less or equal to BWT. This is infinity. I apologize. So we can see that the orange one, so basically this is xt equal to mu over sigma square R WT. Okay. So this is called the Mertens ratio. And this one, the green one, so we choose B equal to 1/2 mu over sigma square R. So this one is indeed xt equal to 1/2 mu over sigma square R WT. And this one, the blue one, is the case that xt in between 0 to L. So we see that after W star, so we know that equal to L, right? Because it entered the constraint domain. So from this graph, it is not clear if how the x looks, how the x behaves here, right? Because it seems like this blue line is also a straight line. So in order to verify this, we simply do this x over w, right? If it is a straight line, then x over w is a constant, right? But the next graph will show that this is not the case. So we will see that again, so this model is case 3, xt in between 0 and L. So benchmark is case 1. So xt is 0 to infinity. So BPC is case 2, xt greater to 0, less or equal to 1/2 mu over sigma square R WT. So we know that this case and this case, this is case 1, case 2, they are all constant. And from here, indeed, we will see that it first decrease until W star and then decrease, right? After this W star, we know that X star simply equal to L. So X over W is simply L over W, right? So this is L over W. And indeed, when we calculate this numerical one, what we got is, so we know that this is the unconstrained, this is the constraint domain. This is the unconstrained domain. So this is W star. So there's one critical point that how to determine this W star, right? So indeed, on the right-hand side, if we take a look back to the ODE, this is a standard ODE, right? This is the standard second order ODE. So it has the explicit solution. So for the right-hand side to infinity, once W star is given, we can get what is VW star, what is V prime W star. Okay, so the only free variable on the right-hand side is W star. But we also know that, for example, when R less than 1, we will simply know that V0 is simply 0. When R indeed greater than 1, we will show that V0 equal to negative infinity. So indeed, in the case that this one, this is easy to calculate. This is easy to, calculate for numerically. So with this V0 equal to 0, VW star and this V prime W star, we can do numerically to determine a unique W star such that this all works. So basically, what we did is we use this as the boundary condition on the right-hand side for this unconstrained domain, and we compute leftward. So in the end, we plot this W star. This is V0. So we see that it's a decreasing function. So it is easy to decide that for this W star, when V0 is close to 0, as close as possible, and we determine that W star. Okay. And also a last graph is like if we increase L, so this is a benchmark. So benchmark is always the largest one. So this is xt equal to mu over sigma square RWT. So this model one is with xt greater or equal to 0, less or equal to L1. So this is xt greater or equal to 0, less or equal to L2. So L1 less than L2. Okay. So if we increase L, then the W star will also increase. So basically, this is what we want to show for this graph. Okay, so thank you very much for your attention. Okay, and thank you very much for your time. Yeah.
Thank you very much, Zimu.